All right, greetings, everybody. My name is Peter Dyke, and I'm the Executive Director of the Alliance for PE Pipe. Welcome to this edition of our webinar program, where today we're going to be talking in great detail about open cut construction. And we are committed to doing this session once a year, and we'll update it with new content every year. You know, every year we do, what is it? I think 15 different webinars, and it's going to be one of them every year, we think. Before we get started today, as more and more people come in, we've got a couple hundred right now, we'll probably expect another 100 or so. I just want to take a moment to thank the companies that make this possible. The companies on this page contribute financially to our operation every year, and we couldn't do it without them. And of course, as you know, there's no cost to you to receive these PDHs if you're engineers. So we're very thankful for our members that are helping us produce this webinar program. For those of you that are into social media, we are here at the Alliance for sure. We publish every day on our social media channels. LinkedIn is the most interactive and most successful of those platforms. So check us out if you can. And if you're in any of these areas, we would love to see you in person. We have quite an in-person program to supplement this online presence, and we're very active. We saw over 225 people in Lincoln, Nebraska, Omaha, and Lenexa, Kansas last week in an excellent series of shows with our good friends at Core and Maine. And then my engineers, Dan Landy and Alan Ambler, have quite the program going with seminars as well as project assistance. So if you're one of those engineers that's got a project coming up and either you don't want to let the client know you don't know something, or you honestly want to check something out, we'd love to help you. And there is no charge for that service. And once again, we thank our members for that. And if you haven't heard, Alan Ambler completed the latest revamp. Alan, come on if you don't mind. Tell us a little bit about the specifications that you've updated for 2024.
All right, Pete, I'd love to tell you about it. We certainly updated it with additional testing measures. So that is going to be pressure testing, fairly detailed from ASTM, also the guided side bend back test and how to execute those and when to execute those. And then we have the robust set of open cut construction, embedment, backfill, horizontal directional drill, slip lining, compressive fit slip lining, pipe bursting, both for potable water and for sewer, and they're all broken out as PDFs and Word documents, Pete.
Yeah, and that's a heck of a program, and you're getting a lot of play with that, Alan. And even though people may not say thank you, I'm saying thank you today for doing a great job with that. And Dan Landy, come on if you don't mind, and tell us about that engineers package.
Yeah, so there's going to be a lot of references in this presentation as well as the rest of our presentations. And it's a lot to take away from an hour-and-a-half call or an hour and 15 minutes. So we have combined all the resources we want you guys to be aware of into one engineering package. If you don't have a lot of experience designing with polyethylene, it can also really help you quickly adapt your AutoCAD drawings. So everything involved in the design phase can really be supplemented by our engineers package.
Yeah, and that's great. And we're always working on that. So Alan and I are working on this Engineers Without Borders project in Peru. And, we'd love it if you'd share $10 with us so we can help fund this program. But anyway, we are helping a community. WL Plastics is donating the pipe. McElroy is giving us a 2.6 machine so we can do the fusions. And the industry is coming together to help these folks, and we're helping about 400 different families in this neighborhood of the mountains of Peru with clean water. Very excited about it. Alan and I have a meeting with them tonight. So Engineers Without Borders, Washington, D.C. chapter, give us $10. That's all the money that we'll ask for today. Richard Brand, would you please come on and tell us a little bit about who you are and what you do? You are our special featured speaker today. Richard Brand, East Windsor, MUA, come on.
Thanks, Pete. My name's Richard Brand. I'm the executive director here at East Windsor Municipal Utilities Authority in New Jersey. We're about 20 miles east of Trenton. We have fully adopted HDP pipe, going back probably about 12 years ago. We require all developers, all new development coming in to, use, HDP pipe. So
Yeah,
it's-
and
it-
you have spoken at several of our events over the years, and we so thank you for coming on today and sharing with this audience certainly your experiences in New Jersey, because I think they're pretty typical, Richard. You've had to train up the contractor community, but you've also had to get a lot of people on board with going with HDPE. Am I right?
Yes. Yep. We ran into a couple obstacles. At first, we seem to have them straightened out now. Every once in a while, we do get a general contractor that needs to be pushed back. But when we first originally started, it was, the toughest part was getting people certified. And thanks to the Alliance and, also ISCO, who came out and helped us get our contractors trained, we seem to have alleviate that issue.
Yeah, we
Uh,
did a great job with it. And I know Greg Elwood at ISCO was instrumental.
Yes.
Certainly, we did some road shows with him, and that's kind of how it goes. We met each other at an AWWA event, and then you invited us to come with our truck with 10,000 pounds of gear, and off we went. And that was like a decade ago. So
Yeah.
please come on when your slides start showing up, and can't wait to hear from you today.
Sure. Thank you.
And then I also like to acknowledge these folks who are working our bench today. We'd like to say that we're running two separate programs. We're running the open cut deck, and at the same time, we've got, hey, ask whatever question you have related to polyethylene pipe, and these guys will be there for you. So Dustin Langston with WL, Chris Waite with Secor, a distributor that we just did two cool road shows with in South Dakota and Wyoming. Mike Whitehouse at ISCO, and then, of course, our very own Dan Landy. So, Alan Ambler, would you like to come on and pick it up where I leave it off? I'd appreciate it. Tell us about yourself.
Okay, I'm Alan Ambler, and Pete and I spend a whole lot of time providing this education for everyone out there. So I ran a utility for the city of Castleberry for almost 10 years, and that's in Orlando, Florida, where I'm projecting from today. And then other than that, we interface quite a bit with lots of different engineers all throughout the country. So pretty cool to be in that position, to be able to share those experiences in engineering or in life. We learn from failure more so than we do from success, but sometimes it's easier to learn from someone else's failure. So we'll include those personal anecdotes as we go through.
Yeah. All right. Well, thank you, Alan, and I'll fade into the background.
Okay, so what we're looking at here is a fairly big paradigm shift from installation of pipe yesterday to what we see installation of pipe today. So lots of different technologies have changed. Lots of trenchless technologies take advantage of long longitudinal lengths for us. And then also we're using new materials that had been continuing to innovate. So what you'll see on the right seems like this pipe could be under some type of stress. It was forcefully pushed into this alignment in this position, but then after that pressure and that force was relieved, rather than pressure, force, then this pipe goes through what's called stress relaxation. So it becomes a happy pipe. And in doing so, we avoid all those bends and all those otherwise fittings that would be necessary. So over time, the way that we have conveyed water has changed, as you're seeing here. Some of you out there in the interweb there still have wood pipe that are operating within your systems. Gentleman from yesterday's webinar in Montana had indicated that they're still very much using wood pipe, and I believe Richard might have a story about that too later. So clay and asbestos came about. Asbestos cement pipe was really increased in popularity during World War II is all of that metal was going to the war machine and going overseas. Just to make it easy for those that are not aware, ductile iron, PVC, and HDPE were all invented and brought to market about the same time. One of the big differences of HDPE use was it was focused in mining operations in natural gas. A big difference in leaks and failures in natural gases. You leak natural gas and houses can blow up and people can die, and then not so in water. So it's not inferior. It's less used in the municipal water and wastewater products and markets, and that's why we're here talking about it. So for anybody that wants to tune out from calculations, 95% of the installs are going to fall within what's called a design window in AWWA's M55 manual. And that happens to be if you have a DR7 to a DR21 pipe and it's installed with minimum 2 feet of cover for no H20 loading, or 3 feet of cover for an H20 loading. That's a box truck going over top of the pipe. And then no greater than a 25-foot depth, then you don't need to do any calcs. We're going to save the calculations for the end of this presentation. So if you definitely want to see those calculations, we're definitely going to provide that for you as we go through. But here's some of the other things that we see and need in the meantime. So that trench width requirement, Pete, if you want to go back, we're looking at 3 to 24-inch pipe to have an OD of the pipe plus 12 inches. So these are going to be the bucket size as we're going through. And what we're seeing here happens to be a trench that is not too wide. We're finding productivity. Nobody needs to get in the trench because we've already fused that pipe above ground. And then we're saving fairly significant effort by eliminating trench shoring and all those types of things. And when we look at particle sizes, so this is the crushed stone or 57 stone that can be used to stabilize the bottom of the excavation. When we're starting to dig, we sometimes, if we have groundwater presence, have to stabilize the bottom of that trench, over excavate to be able to put 57 stone down and maybe a dewatering unit. That 3/4 inch particle size is perfectly okay to be embedded around a 6 to 8 inch pipe. Then when we get into bigger, so that 16-inch pipe, we can look at 1.5 inch particle size. So we're seeing a lot of this installed this way, just the same way that you would be installing ductile iron or PVC pipe. They're considered to be all flexible pipe materials. Now, this video may very well have some people cringing out there, but this is a perfectly acceptable way to be able to pour that embedment back in a lift. The machine is advancing. The fella in the trench and tells that machine operator just when that lift is appropriate. So we're going to look at 1-foot lifts that you would be able to backfill back on top of the pipe. The reason why we limit it to that is because the compactor can only get so far through that, and we want to make sure that we have appropriate density through it. So here, it's a pretty simple operation through this. They started to excavate, laid down proper bedding for the pipe, then bring back that embedment around the pipe and start to backfill it. So it's pretty effective for the 2 employees you're seeing here. Okay, when I mentioned paradigm shift, if we can open up more trench and all of a sudden put that long fused up pipe run already in the longer area, we're going to dramatically increase our productivity. And that just means that that contractor gets paid more because he gets paid or she gets paid based on how much pipe they're putting in the ground. So we're going to start to see a paradigm shift for contractors that are aware of the benefit in increased productivity of a long fused run, really start to take advantage of that for their own needs. Here's that picture again on the right. So that contractor knew that they could open up a longer, larger area, and they're starting to make use of that as well. So you'd have take advantage of the productivity tools to fuse up runs above ground in a laydown yard, either close to the project site or within applicable distance that you could pull that into place. And then you start to fuse up that long run, open your excavations as we go through, simply drop that pipe into the excavated hole and start to move forward from there. You'll see in the picture on the right too, that 57 stone stabilizing the bottom of the trench. And then they're taking advantage of not having to put anybody in there to minimize that width. Okay, here's another example. This is from Austin, Minnesota. This is in-house crews in Austin, and what they've decided to do is use a slash and burn method, for lack of a better term, to open up an entire block and replace all of the infrastructure at the same time. So they are doing large excavations to replace both the potable water, the gravity sewer, as they're seeing that not in a common trench, but they recognize with the neighborhood that they're going to have an impact, and then they simply limit that impact and replace all of that at the same time. Advance. Okay, so one of the big time requirements on the job site is actually making that excavation and backfilling it. When we're limited in traffic areas, actually moving that MOT out. That's a video, Pete, if you want to play that as well. So moving that MOT out into the roadway to be able to protect the people that are working on it takes a fairly significant amount of time. This contractor in the video you see on the left in Tucson, Arizona, recognized that, hey, we're going to have to shut down part of this road anyway. Let's do that MOT for a longer distance and simply recognize that we can go through and excavate and install that long run of pipe for a higher productivity. In the picture on the right for a City of Tampa job here project, they were using pipe bursting to be able to replace an existing cast iron main, but you still have to make excavations. The actual act of moving that MOT out into traffic and taking it away took up 1 hour of their limited 10-hour window for construction. Then moving the construction excavators to the pit size and taking them away also took another hour. So 20% of the productivity, the job site day allowance that they had was just getting the equipment to and from. Yes, Pete.
You know, Alan, I've heard this argument several times from people that aren't used to using polyethylene. Contractors that are used to using it embrace this long laydown area. Those that do not or are suspect of it suggest that a long laydown area equals a larger footprint, therefore it's not ideal. They're actually correct because it is a larger footprint, but it's so brief. Can you share with our audience your perspective of that and how that makes sense in an overall construction cycle like this?
Sure. So we often don't get to look at the social benefits of not being in front of residents and customers. And if we can maximize that productivity, now your crew simply won't be in front of your residents and customers, so there won't be that type of an impact. That's a definite benefit for maximizing that productivity by installing a whole lot of pipe at one time. And yes, you're expanding that construction zone, as you did recognize, Pete, but by being able to put in more finished product at the same time, we're certainly maximizing that productivity.
Well, certainly it's more pipe quicker, but we're also seeing a benefit in much shorter construction cycles. Like even if it's open cut, Alan, I'm seeing half the amount of time versus traditional methods. At least that's what I get. What do you hear?
Oh yeah, it really depends a lot on limitations as to if you have road crossings or if your project specifics. But less time for the crew to actually be on site means definitely greater cost efficiency. So I'm hoping I'm answering your question pretty well there, Pete, in that manner. But yes, that paradigm shift, higher productivity is going to make cost less to construct the project, make that contractor more money, and keep everybody a little happier.
Yeah, that narrow trench width is pretty huge as well. I mean, even, Alan, 50% of our jobs are open cut, right? And all of the open cut ones, or most of them, unless we get the really big ones, we're looking at a much more narrow trench, therefore less cut, less fill, less time. Is that right?
Yep. Mm-hmm.
All right, take it away. Thank you.
So in the trenches now, we're going to go through a whole series of pictures for you pretty quickly as to how to actually get in that trench and perform the work necessary. First and foremost, drag chainsaw is one of the ways that we use to manipulate and work with this rugged and durable product. We use oilless chainsaws. While it dull the blade a little sooner, it won't contaminate that pipe for what we need. You simply just cut right through this. The Alliance Road shows we use a jigsaw or something else of that nature. So next one, how do we get that butt fusion in the trench? All of the machines are designed to do this. It's designed to get that butt fusion machine off of the chassis and be able to put that down in the excavation to perform that fusion. So here's a whole series of pictures to show you with various trenching and shoring applications of how to get that into that excavation to perform that final fusion in that manner. These are final connections when we need to perform that final connection and button things back up and get out of the job. So here's just some more examples from McElroy directly on how this equipment gets lowered down into the trench and set up and how you're working with it. All of the aspects of fusion are the same. They're doing the same tasks. That machine, now that it's in the excavation, is still facing the pipe, making sure that you get back to virgin resin, heating up the pipe ends to the appropriate temperature for the appropriate amount of time to get back to that molecular level, and then boom, you're forming that face together and you're pushing that pipe to allow those molecules to flow across that interface to give us that joint that is as strong, if not stronger, than the pipe itself. And Pete, I could tell you have a dying question for me
here. We have a lingering question here. A audience member asked, can you please explain how we're supposed to get the stone into the haunch area?
So for larger pipe, this becomes a much bigger problem. Obviously, with larger pipe, the logistics of being able to get all of that together in those areas becomes more challenging as we see it. So for the haunch area, for a smaller diameter pipe, a lot of things will settle right down into that area. The workers themselves can go through and support that. The compaction around the edges obviously is a long-term thing for any type of compaction, especially up against manhole edges or anything of that nature. Once that 57 stone settles around in the haunch of the bottom of the pipe, most of the protection is going to be provided by compaction of that backfill that's on top of it in that manner. So hopefully that helped answer the question. For larger pipe, obviously you're going to have more effort, larger, wider trenches to be able to get access to the haunch and make sure that we compact that. So good, Pete, I'm glad you've been going through these images. A lot of them are much the same. We're simply getting to where we need to line up that butt fusion in the end, and then lowering that machine down into the excavation. You'll see a slide rail system here on the left that provides access to it. All trenching aspects and shoring devices, again, are providing a safe environment for the workers to perform the work, more so than a wide environment for the pipe itself. Yes, Pete.
So what I love about these couple of images that you put in there on the right, the middle and the right, is that not only can you take these machines and put them in the trench to complete a tie-in or effect a repair, the one in the middle shows 3 jaws versus 4. So that means the tech is getting ready to do a 45 or a 90, something like that, or some other spool or fabrication. And then on the right, when we get to the really large diameters, we go back down, Alan, from 4 jaws down to 2. So that on the right looks like about a 54-inch diameter. And these really large McElroy machines then get down to the 2 jaws, and they require then extra machinery to help elevate the pipe or other equipment so that it doesn't apply torque into that fusion zone during a fusion.
That's right. So good observation, Pete. When we get into the really big pipe and we start to see the larger McElroy equipment, that equipment is going to do a lot of the work for you because it's big pipe. So here's just a couple more images as we're moving forward, really cruising right through this. We'll talk about electrofusion. And in some instances, that electrofusion coupling is the right tool for the project area. Now, we're doing the same thing to the resin that we would do in butt fusion or extrusion of the pipe. We are getting down to virgin resin material, heating it up to the appropriate temperatures and allowing that to flow across that molecule, the molecules to flow across that interface to be able to have cool HDPE pipe for that joint to be as strong, if not stronger than the pipe itself. So these couplers are going to help us in tighter quarters when we don't have as much room to work or we don't have as much movement of the pipe to be able to give us access for that butt fusion machine. What you'll see on the left there becomes an electrofusion spool piece that was used as a repair. So we'll have 2 couplers, and then they'll make sure that we can get that right length of pipe in the middle. They'll push that coupler across the pipe that they're fusing to. Then they'll line up the pipe ends at the appropriate location and bring that coupler back to be able to perform that. These electrofusion fittings, they need a little bit more operator involvement in preparation of the pipe surfaces to be able to get back down to that virgin resin material. All they're doing here is connecting to the fitting with the electrofusion processor. They scan a barcode, and then everyone's fittings across the entire industry are recognizable from that barcode. That processor will fuse that electrofusion fitting for the right amount of time needed to be able to get you to moving that molten material across. Yes, Pete.
So in that center image, what the tech has done is he has electrofused a mechanical joint adapter onto the end of that horizontal directional drill in preparation for either a valve or a hydrant. And then on the one on the right, Alan, can you tell us why is it we need a bag on the ends of that spool piece as we're getting it ready to drop it in?
So we want to try to keep that surface and that interface, that fitting, free and clear of any type of debris or anything else like that. So the fittings come in a bag. We do all the measurements, measure twice, cut once type of thing in advance of opening the bag. And then when we're ready to put that fitting on, after the pipe has been properly prepped, then boom, we pull it out of the bag and we make our fusion connection in that manner. So if we'll go to the next one, we'll see T's. These are service connections. Those particular can be put onto the pipe. They're a fitting there to be able to provide us what you'll see on the right then is a self-tapping service saddle as well. So it'll cut down into the coupon. So we'll cut out the external wall of the pipe and it'll hold that coupon in the fitting itself, giving us the ability to live tap a water main in this scenario. The center image shows just a side tap to do the same exact thing for another service connection as we keep going. So lots of fittings available to you. If you happen to be in a position to see one of our road shows, we'll have all those everywhere on the tables for you to be able to touch and feel. You'll see in the bottom picture here's an electrofusion restraint that later can be embedded into concrete to give pull-out force resistance if we're connecting to legacy bell and spigot material. So go ahead and advance. Here's some other ways to be able to connect to that main through service connections, fittings, and other things of that nature. So what you'll see in the right is that self-tapping T, and then that connects to a reducer and connects to an electrofusion fitting and then goes straight to the service connection itself. And you'll see on the left there, we're butt fusing directly to a fitting in that manner. Yes, Pete?
You know, I think we've learned a lot on the road the last couple of years, Alan, and that is, you know, we've shown some self-tapping electrofusion connections to the main, but Alan, there's still a lot of utilities that are intent upon using mechanical connections on the polyethylene mains. Can you share a few words about that?
Sure. In Castleberry, Pete, when we were doing all of our large pipe bursting projects, we did use mechanical fittings. We did not have corrosive soil environments as much. So that fitting then certainly operated on the HDPE pipe in an easy manner. One of the things about a non-corrosive system, such as HDPE pipe, if we put a metallic fitting on there in corrosive soils, then that metallic fitting becomes our sacrificial corrosion location. So that's basically where the electrolysis, for lack of a better word, the movement of energy within that soil is going to go and focus on that mechanical piece. Yes, Pete.
Yeah, I tend to look at it as a transition. You know, Castleberry now uses electrofusion connections. And a lot of utilities, before they get fully comfortable with electrofusion, they make they solve the big question by using polyethylene mains, but then they still use mechanical. That image on the right is kind of an interesting one too. It's a self-tapping electrofusion saddle, and you just unscrew that top and cut into the wall as Alan described. And then it looks like a 2-inch outlet on it. So it looks like a 6x2 that's been that's been butt fused right here to a reducer. And that reducer goes from 2 inches down to 1 inch. And that 1-inch service connection is electrofused onto that reducer. And then we have tracer wire on that 1-inch service going up to the house. And you notice that we have a blue stripe main as well as a blue stripe service. We can make these so that you can transition to your sorry, I got out of whack, to your copper service if you'd like. It's all part of the deal. And we have about any alternative for that connection that you would like. Take it away,
Okay.
Alan.
Yeah, thank you. So now we'll talk just briefly about trench shoring scenarios as well. So none of this would be, any of the OSHA regulations. We won't get into that. We'll just show you some different examples on ways to be able to shore this and get that HDPE pipe in there. So we're looking at sloping is a larger excavation, a larger area, shoring, hydraulic or otherwise, and shielding, trench boxes and combinations thereof. I need to move a little quicker here so we can get to Richard as well. So here's just some more examples of how we're putting that pipe in these excavations. Obviously, the sloping has a larger footprint. And in this picture in Duluth, Minnesota on the right, they recognized they had to shut that road down in order to be able to build this pipeline in place as they go through. Keep going. So smaller excavations as we get through can use that hydraulic trench shoring. So they'll have plates up there, and then they'll push that out to make sure that to provide safe access to the excavation itself. Rental companies will have a lot of these. So that contractor will know that they need to be able to get access to it. When we're talking about that paradigm shift, you may have to rent more trench boxes or shoring, but at the end of the day, you'll be able to get that higher productivity as well. So that safe environment is really set for the workers to be able to perform the work surrounding that pipe. Again, it's not for the pipe's sake, perchance, but it is to be able to make sure we have a safe environment. Keep going. Shielding is another version of that trench shoring itself. This is a pipe bursting project as to which they're starting to get an excavation to get access to an existing pipe and simply pushing that pipe into place. Here's a few other examples for larger involvement for a manhole, a polyethylene manhole in Beaufort Jasper County Water and Sewer Authority on the right. And simply as we get into that larger excavation, now the means and methods to be able to get safe access just grow. They just get bigger. Isn't that right, Pete?
Many of our member companies, Alan, are getting big into this game of polyethylene manholes. You know, I didn't think 10 years ago when I started talking about them that they'd be that big of a deal. But a lot of our companies, Alan, are reporting that they're making a ton of these things, and owners are getting a lot of problems solved because they don't have any more concrete in that ground.
Absolutely. So just like your precast concrete manholes, you need to know what angle, what invert elevation that pipe is coming to through a gravity sewer. So we're going to measure all of that stuff in advance. Then it'd be fabricated off site and brought to your project site. They're going to do the same thing with a HDP manhole. We're just now all of those spots where we have corrosion from force mains dumping into the manhole. You can use that HDPE manhole to be able to get access to it. So when we're starting to get deeper, now it gets more complex. This is a shoring slide rail system, be able to provide access to that excavation as we continue to go through, and of course temporary sheet pile to be able to get access as well. So the deeper excavations, now we're starting to incrementally increase the cost of that excavation. So if we are able to use a trenchless technology that eliminates the cost or eliminates more excavations as we go through, then we obviously are going to be able to minimize that as well. But all of those parts and pieces, again, fit into that excavation. They come off of the chassis. Hate to continue to say the message, but it's very much true that these tools are designed for this purpose and to work with you. So Richard, do you want to come on and tell us about your experience at East Windsor?
Sure.
Turn it
Thank
over to
you,
you, Pete.
Thank you, Alan. I appreciate it. And that was a great presentation. Okay, here at East Windsor, we're a 25 square mile community, have a population of about 30,000. We have approximately 230 miles of water main. On this picture here, you see that we have AC pipe, ductile iron, cast iron, high density polyethylene. We have a little bit of C900, and we also have some pre-stressed concrete pipe. So we have a little bit of a mixed bag. Here during the 1960s and 70s, when we were first built, we have approximately 56 miles of asbestos cement pipe. During the 70s, all the way through 2010, was the installation of ductile iron. During the 70s and 80s, we put in 84 miles of pipe, and between 1990 and 2010, with the development surge that we had at that time, we put in 68 miles of ductile iron pipe. From 2010 to 2023, right now, currently, we have approximately 37 miles of high-density polyethylene. Okay, if you look at this graph, you'll see that with the ductile iron, we replaced approximately 15 miles of ductile iron pipe that has failed on us. We here have our soils are hot soils. We have clay soils, black loam, which is really acidic soils. So it attacks the pipe from the outside. We also have underground cables from our utility provider, which also causes electrolysis and attacks all of our metallic pipes. Okay, slide. Okay, here's the life cycle of our pipe. If you look back with the late 50s and early 60s, that's our AC pipe. That is coming up of age, but has not, knock on wood, has not failed us at this point. The pipe that has failed us is our metallic pipe. So that's what we're focusing on now. We're currently at this point, we're looking at replacing approximately 2.5 miles of pipe per year.
So Richard, you say you're getting better service out of your AC pipe than you have your ductile iron.
Yeah.
Have you wrapped your ductile in polyethylene?
Never. No, it's not, I'm not a big fan of wrapping it. Number one is you got to make sure the contractors, when they're installing it, are handling it with care. Most of the time they're not. It's all about time. Let's get it in. What happens is the bags get ripped or torn, and they're not secured. So then you get leakage. Not only that, I've worked in communities that have had wrapped ductile iron pipe, and when you have a break, you're chasing it because it expands into the bag, and then it finds the least path of resistance, which could be a rip or a tear 20 feet up the road. So
Right.
you end up chasing it, and it costs you more in the repair of the road than it does in the repair of the main.
Interesting. Dan, please add some comment.
Yeah, Richard, pivoting topics really quickly. We got a great question while Alan was presenting, and I'm hoping you might have some insight. Now that you guys have gone to a fully HDP system, do you separate in the trench polyethylene and for water and wastewater? Do you still have to worry about that separation?
Not necessarily. We still follow it. We still follow the rules for it. But you don't have to because there is no joint. So if you have a full length of pipe, you can cross a sewer line with the water line and not worry about any cross contamination. So it does eliminate that issue.
Okay, so do you still think the hurdle is still there for separation just in terms of what the norm currently exists and getting approvals?
No, no, I would
Okay,
say,
so if you wanted to, you could do that yourself?
yes.
Okay, thank you.
Alan, you were in Omaha last week. We heard some pretty interesting things from Jared Figuera about his ductile wrapping issue. And the reason I'm kind of interested in talking about this isn't because I want to bash ductile. It's just they have been very clear that they have solved this issue of tuberculation, and that new polyethylene, new ductile is just as good as polyethylene. Could you give us some color, Alan?
Sure, sure. So the Water Research Foundation has studied corrosion in metallic pipes fairly significantly. They have a Water Research Foundation report that states that in highly aggressive soil or corrosive soil environments, they can expect to get full pipe wall penetration of new ductile within 5 years. So that's a leak within 5 years, right on that pipe. So some of the things that in the next slide, Richard's been looking at as common failure mechanisms. They suggest to wrap that pipe in polyethylene. It's called the V-BioWrap or something like that. And if you do not, exactly what Richard said, if you do not take proper care and make sure that that wrap is secured on there with a table that shows you how much duct tape you got to use and in what intervals, if somebody even walks on that pipe with that wrap on it, they can cause a tear in that pipe. And now we're focusing all of that electrolysis, as Richard said, in that one location. So you got to take real good care with it. And it's not just Richard that's experiencing this, especially in corrosive soil environments.
Well, yeah, Jared also said that, they have 3,200 miles of water main, and they're getting longer life out of their non-wrapped ductile than they are their wrapped ductile. I mean, I'm what? So that's interesting. It's not like they're making it up. So Richard, you're not alone.
Yeah. Yeah, the wrap is acting as a shield and trapping the water inside where the pipe is and the corrosion.
So Richard, you as an engineer are also the executive director of your entity. Did you have any pushback from your elected officials when you decided that perhaps poly was the answer to the issues you were seeing in your town?
No, I gave a demonstration to our board here, and I believe in educating our board members because at the end of the day, they're the ones that make the big decisions on the costly projects. And they've all been very well educated on it. They're fully on board. The issues that I had are mostly with the developers and the general contractors. The general contractors, of course, are the ones that are pushing back with the developers, who are then asking us to allow the use of ductile iron. And we explained to them the reasons why we don't, and why the MUA continues to install just high density polyethylene. So it's I still get my pushbacks every once in a while. There's always a new contractor that comes in, and we are prepared. We warn them well in advance during plan review. Also, when they turn in their submittals and their shop drawings, we review them and we explain to them what we want. On their final plans that are approved, we make sure now that there's notation put on the plans that require all stainless steel bolts. We do not allow steel bolts on any of our equipment here. Any of our appurtenances. All of our hydrants, valves, everything have to have stainless steel bolts on them. So, we do get pushback, but we have a good inspector here that oversees all the projects, and he does a good job.
Yeah, awesome. Well, you've certainly seen failures in your old cast iron, but you're also getting them obviously in your ductile. I think this one's a ductile, isn't it?
Yes, yep, that was from corrosion. You can see the pitting on the outside of the pipe, and that's from the hot soils. And this particular pipe is only 40 years old.
Wow. All right, back to you.
Okay, again, here we have 230 miles of pipe. Our miles that we are replacing currently is about 2.5 miles per year. Our average breaks right now are about 8 breaks per year, and it used to be up around 16 to 20 breaks per year. But we hit all of our hot areas with the high density polyethylene. We replaced all of our bad, our hot spots that were ductile iron. We replaced them with the high density polyethylene. And as you can see now, our break rate has dropped. Our water rate loss was up around 15%. We're right now down around 6.5. So it's, we've been moving in a positive direction. And we believe the life cycle, even though I have 80 years here, we believe on the high density polyethylene, we're going to be getting 120 years plus out of this pipeline.
Well, that's interesting that you say that. So, a lot of people say to me when I'm out there talking about this, Richard, that, well, your pipe hasn't been in the ground, so how do you know how long it lasts? So the UKWIR, which is the United Kingdom's version of AWWA, published a report 3 years ago now, where they exhumed first and second generation polyethylene pipe. So I say it's first and second generation resin that was extruded into polyethylene pipe. And they tested it, Richard, and they said its life would be 160 years.
Yeah.
And we, at this point, we kind of say hundreds of years, but
Right.
both PVC and ductile and polyethylene, all of us say we have 100-year pipe. So although we haven't seen it for 100 years, 50-year-old polyethylene pipe that was exhumed, tested new, and they said it would last probably 160 years. Dan Landy.
Yeah, not to hold you up, Richard. We got a quick question on what methodology and technology are you guys utilizing to perform condition assessment?
Okay.
What we on our condition assessment on the pipe, we have taken we have cut pieces of pipe out of the system and had it tested. That was about 10, 12 years ago we did that. But a lot of our assessment has been by our crews out in the field. We're out there and they're, we get a water main break. They're out there. I would say good 70% of our breaks right now are circular breaks, and that's due to the freeze thaw of the environment, the climate that we're in. here in New Jersey. Our frost line is approximately 3.5 feet deep. So, and our pipes are roughly about 4 feet down. But we're getting movement in the ground, and it always happens when we get a quick temperature change. So that's really what's driving this. With high density polyethylene, we're not going to see those circular breaks anymore. You know, the pipe is made for seismic movement. So, you know, we're eliminating that. We're eliminating tuberculation. You know, we're eliminating everything that we have here. So, at the end of the day, our pipe system can withstand any of the environment that we offer here in East Windsor.
So in this image, I see that you've asked your contractors to label your pipe strings. Tell us about that. How does that work?
Yes, when they do the installation in any of the butt fusion, they're required to put their I think it's their license number on there, stuff like that, so that if there is ever a problem or a failure, we know where it was and who did it, so we can go back and find out. We also use a data logger also on all of our butt joints, so you know, that tells us everything, you know, out in the field anyway.
Sure. You know, that data logger, Richard, now the new upgrade of it, or the new software, it's kind of like Tesla. They send out these new upgrades. It permits you to do pressure tests. When you do one of those hydro tests,
Yeah.
you can hook it into, Dan Landy's got a presentation on this. You hook it into that pipe string, and it reads the pressure, so that you can document the pressure testing on those pipe strings.
Uh-huh.
Alan Ambler.
Hey, Pete. Yeah, I'm glad we're talking about testing. We just got a great question on destructive HDPE joint testing. So there are different tests that you can do to validate the fusion zone, the fusion operator, and the equipment doing it. One is called a guided side bend back test that you can do, and definitely reach out to the Alliance for PE Pipe for the specifications on how to do that. Check out our YouTube channel as well for different videos on how to perform that. So we're about 2:51 now. This webinar does go for 75 minutes. So we'll go up to 3:15 Eastern Standard Time. And we've had well over 45 questions. So keep them coming, guys. Great job.
Yeah, thanks to the bench for doing that work. Quick reminder, all the Alliance webinars are 75 minutes, and the bench will answer any polyethylene related question that you have. So we have a good 25 minutes left in this webinar, and we're right on schedule. So Richard, are you requiring that contractor to upload those data logger reports so that you guys can review them before that pipe string goes in the ground?
Yes.
And did you train your inspector on how to read those reports?
Yes, he has been trained on it. Yes.
Awesome. Well, that's an important skill.
Yep.
I'd also like to advise our guests that today we ran a training video before we start the event, and we're going to do this on every Alliance webinar going forward. So we'll have a 5 to 10 minute pre-show video that covers a topic of interest. Take it away, Richard.
Yeah, this particular project here was a directional drill going underneath the New Jersey Turnpike Authority during it's about 7 years ago, 7 years ago, they did a big major widening down the turnpike. And because of that, they had to relocate some of our lines. We had a forced sewer main that was alongside of one of the bridges that they had to remove. So for that project, they paid for the removal of the force main and the installation of a new polyethylene, high density polyethylene force main to replace the old AC pipe that was there. But also at the same time, since they were doing it, we did a share with them on installing a new water main. So this was an 18-inch high density polyethylene water main, about a mile long. Okay, here you can see Kate Metz was the contractor. He was a good contractor. We had nothing but good praise with him. He's done a lot of this kind of work. And the project worked out very well. Here you can see the steel casing. Unfortunately, the turnpike did require us to case the line going down underneath the turnpike. Our water line is about 35 feet under the roadway. That was a requirement of the turnpike. So here you could see the lengths of steel that were welded and ready to be pulled through. And on the bottom low picture, obviously you see the polyethylene pipe being encased by the steel. Okay, this was a township it's a project that we did ourselves here on Greenwich Court. Our contractor here, again, you can see the trenching and the bedding. Here we require sand bedding. We require 1 foot below and a foot above the crown of the pipe. Once that's been done, then we require marker balls to be placed every 20 feet. Those marker balls are able us to identify and locate the pipe. We also use tracer wire, and then we also use metal marking tape. Okay, on this picture here, this was Greenwich Court. Again, this reason why we do mostly open cut here is because we have high density housing. Our service lines are spaced approximately 20 to 30 feet apart. So even though we have to go in and tear up the road, that's why we decided to use with open cut. Here you can see an electrofusion saddle being performed. Okay, this is our one of our barns, our training shop right now. We're in the midst of we're in the final of the approvals from DEP on building a new administration building, maintenance building, and water treatment facility. In that maintenance building, we are going to have a big training class for our employees. But here, this picture shows that we bought a Track 618 butt fusion machine. Our guys have been trained on it, and we're getting out, getting ready to install a bunch of water mains. Here again, this is the guys practicing. They're cutting pieces of pipe right now, practicing on getting out there and performing the work. Okay, this is the future site of our water treatment plant, admin building and maintenance building. Here our guys are going to be installing 4,800 linear feet of 16-inch DR11, blue striped, also 400 linear feet of 24-inch DR11, and about 1,200 feet of 8-inch DR11.
Wow, that's exciting. You're building a new plant and you're going to use polyethylene outside the building. You know, Richard, we get a lot of pushback from people saying, oh, I've got to buy that fancy machine that you bought. You know, well, you're going to get a lot of use out of that machine, but how do you answer that you know, the training involved and the capital equipment? You know, you've taken polyethylene to a level where not only are you hiring contractors to do it, but you're using your own guys to do it. How do you address those questions that you get?
Well, it's well worth the investment. We had in one of our sections, we had a contractor come in and install the water line. Cost us $1.5 million for about a mile of pipe. And that was a mixture of 10-inch, 8-inch, and obviously some 6-inch laterals for our hydrants. Out of that, the material itself cost about $300,000. So if you look at it, you see you got a $1.2 million profit that contractor walked away with. I could take that 1.2 million. I can buy a brand new track machine, which we did. We can buy a brand new track hoe, which we did. And we can install it ourselves. And the one thing is getting our staff to buy in. And here at East Windsor, we believe that, they're saving the MUA a lot of money. So they're entitled to a piece of the pie. We treat our employees very well here. So if you're on the pipe crew, you get a couple dollars more an hour. And everybody is bought in on it. These guys are excited. They've learned a new thing, and they're doing a great job. They really do. I'm proud of them.
We got about 15 minutes left. We're going to end this chapter here, Alan, shortly, and we're going to turn it back over to you. Richard, I have one final question, and that goes to the issue of failure. A lot of people say, oh, yeah, this is what you have to do with polyethylene. You got to clean it, shave it, heat it, fuse it, all that. And there's so much room for error. What kind of error rates are you seeing, and what kind of failure rates are you seeing in your HDPE pipe installations?
Zero now. Zero. We know what to look for. We know what to do. Our guys have been trained. We give them time. Days like today, it's raining. Actually, they're probably listening in right now. But normally, they're out. If it's raining, we bring them into the barn and we have them practice. Training is the utmost importance. And again, with our guys, we're going out, and where we would only be able to afford maybe a half a mile to 3/4 of a mile a year, we're going to be putting in 2.5 miles per year. So we're going to be up above the curve. And at the end of the day, we have a great product. We're all very happy about it. Once we put the high density polyethylene in the ground, we're not coming back. It's done. We move
So
on.
you haven't had any third-party damage yet?
None.
And you haven't had any butt fusion failures or any electrofusion problems?
None. And we've been doing this for 10 years at a steady pace. Prior to that, we used it all for directional drilling. And, again, when you're going underneath a roadway, if you feel that pipe is secure and safe enough to go 35 feet underneath the New Jersey Turnpike or underneath any stream bed or anything like that, then, why don't you put it in your distribution system?
So that's fantastic. Great to hear. Did you fill this annulus with anything?
Yes, we did. Yeah, we used a fillable flow.
Flowable fill? Okay.
Yep.
Fair enough. Hey, great job. If you wouldn't mind hanging around, we might have some more questions for you.
Sure
Alan
will.
Ambler, I'll turn this back over to you.
All right, Pete, great story from Richard. I always love to see it when the municipality itself is doing the actual work. That makes me very happy. So what we're looking here, there's no smoke and mirrors to this as far as excavation is concerned. Your way to install ductile iron, PVC, and HDPE are all going to be the same. So they're flexible pipes. Advance through the full slide for me here, Pete, if you can. They're different from rigid pipe, in which case the flexible pipe forms a pipe soil interface together, and they take any type of loading on top of the pipe and transmit it to the soils that surround that pipe. In rigid pipes, they're expecting that to be way stronger than the soils that surround that pipe, and then that rigid pipe will simply confirm and move all the forces on it down to the soil underneath it. Excuse me. Hard to talk today. There's two characteristics that are primarily and only there for HDPE. That happens to be creep and stress relaxation as we see this. So a creep, basically, if we continue to point load that pipe over all duration, so for an extended period of time, that material will change shape. It will deform. It will move. But if we remove that force after we've bent the pipe, not beyond yield, that pipe will relax in that pattern that we've got, that shape. That's called viscoelastic behavior. That's where the elastic modulus changes over time. That allows us to be able to come around those curves, be rugged and durable in the field, to be able to work with this pipe, pull it into place, and then the pipe relaxes and is able to handle those daily loads as they go through. Keep going. So advance all the way through this one too. If we did not have the soil that surrounded the pipe and we induce a load on it, now we are going to see that creep as we come through, and we'll have deformation of the pipe material. When we have that soil interface surrounding this pipe, if we put that load on it, that load is distributed to the soil surrounding it, and we do not have creep in that manner. So we're going to look at that soil pipe interface, both the pipe stiffness factor and the soil stiffness factor, and kind of guide you through some of the calculations that you'd find in M55 manual in a few. Advance. So the trench behavior that we're looking for here has a bedding, a foundation. The foundation we want to be free and clear of rocks and other things like that. The bedding is simply placed at the bottom of the trench to give a cushion for the pipe, and then we look at that embedment and backfill coming up through the top of the pipe. There's certain things that need to be happening for it as we go through. This is a video for us, Pete, for one of Richard's places there as well. We saw these two workers being able to put that backfill material on top of the pipe before. Now they're simply putting the pipe into the prepared trench that had bedding, which is set there to be able to receive that pipe. Again, we're not putting anybody in the trench in these scenarios, and they're taking advantage of that long, productive run by installing all this at the same time. Go ahead, advance, Pete. So here's that design window. Exactly what I'm telling you. 95% of the installs will be within that DR7 to DR21. So that's a stiff pipe with a minimum of 3 foot of cover for an H20 loading, 2 foot of cover without an H20 loading, and a maximum of 25 feet. You could put back the native backfill, compact it on top of that pipe. Those things will interact and work together to give you protection for that pipe. Advance. What we're looking for here is the DR of the pipe will tell us what the stiffness of the pipe actually is, and then the modulus of that soil reaction. Both of those things work together to be able to distribute those loads. So the modulus of soil reaction increases as our compaction gets better and our material gets better. And then that DR, the pipe stiffness factor, increases as our wall thickness gets thicker. Go ahead.
All right, we're going to take a quick break here. Dan, could you run that poll question? I think we only have one today, and then we'll move through the slides a little bit so people can see what Alan's talking about.
Yeah, you're the host, Pete. It should be on your bottom bar.
All right.
Quizzes.
So the things that we're looking for, well, I saw it, Pete. Good job. You did it. So the things that I'm looking for when we're doing these calculations are deflection. So we're making sure that that pipe, as it's installed, is not going beyond yield for what we're looking at. Wall buckling, so we want it to make sure that you're not crushing it. Unconstrained pipe. So what we're looking for here is that there's not a negative pressure within the pipe to be able to collapse it. Especially with thinner wall pipe, we want to be able to make sure whatever forces that pipe is going to be put under, if it's on a steep slope and we get a break at the end, you could find that type of stuff there. So, and then that last wall compressive stress. So these are all the things that are in the M55 manual that you can calculate. And then Chris, I don't know what the question from was about for bedding, so you'll have to type something in chat for me because I don't have that open. Here we're looking at pipe stiffness factor. So if we go back, that DR 7.3 has a 1600 PSI pipe stiffness factor. The DR 30.25 is only 12.5 PSI. So we're looking at that thinner wall pipe obviously does not have the hoop strength that we're going to do. So here's the modulus of the soil reaction. So this will show you exactly what compaction does for these class levels of materials. We obviously don't want to use a class 5 material, organics or anything else of that nature in any pipe embedment. But as we start to compact that material, that pipe, the soil stiffness factor will certainly be there to help distribute the loads. So that's both of those on the bottom of the equation there, and then go fast forward and we'll get to the top of the equation. And what do we actually see on the pipe itself? So there's tables for the information within M55 manual that'll show us, and I'm moving pretty quick on this one. Go to the next one. So what we're looking at on the top is a live load, an earth load, and a surcharge load. So if we want to look at the effects of that depth on the pipe, at 2 feet, that live load from an H20 box, the Penske truck coming over is going to put 16.8 PSI onto the outside of the pipe. But when we get down to 8 feet depth, that's less than 1 PSI. So the things in a pressurized pipeline, a DR11 with 200 PSI design pressure, that's exponentially higher than the external loads on this pipe. Then we'll look at calculating the earth load, which is just the density of the height of that soil column on top of the pipe. Advance. So here we'll go through this one pretty quickly as well to show some of these calculations. The Alliance for PE Pipe does have these calculators for you. You'll just have to contact Dan Landy and we'll be able to make that happen for you. If you advance all the way through, we're going to show the 4-foot depth of cover on the live load is 16 inches. The external live load PSI is only 4.2 PSI, and we're significantly less than what that DR17 can really see. If we look at the 45-foot depth of cover, live load of 6-inch DR11, the earth load pressure of that soil column will be the highest on top of it, and that's 45 PSI, but it's still significantly less than what the operating pressure is in that manner. So go ahead and fast forward to the next one. Here's an example of wall buckling, and here we're certainly within our allowable size here for PSIs that we're calculating with a 4-foot depth of cover and also 45-foot depth of cover as well. You'll see that's well within the allowable PSI as well. If you go to the next one, we'll show you an unconstrained pipe. So this varies based on the DR of the pipe, of pipe stiffness factor that's bigger. Obviously, we'll be able to resist much more vacuum pressure within the pipe. So if we're looking at a thinner wall pipe, some instances of your operation, you may want to look at this. The wall compressive strength is the last calculation that we'd see here. And then this, we're simply looking at that not collapsing and being able to resist that earth load. So if you want to advance to the next ones, we've got some videos of install and personal anecdotes of people that have installed the pipe. Pete, you want to come on and narrate?
So this we shot in Virginia, Alan, and this is just an idea to give people an idea of what you can do to the polyethylene to get it to go under a crossing utility. In this case, it was a sewer line. It was a low pressure force main, and it wasn't going anywhere. But they had to get that pipe back up to elevation in order to effect a fusion here off on the left. And so it's actually pulling up on that, gosh, Alan, what is that material of that force main? I can't tell.
Yeah, I can't tell either from the image, but this is very common to be able to look at utility conflicts and get over the utility conflict in that area. Creative. Before you play the last video, I'd like to answer one of the questions live. What if the bed for the trench is a level rock like shale or otherwise? Do you still need to bring in the soft bedding? The soft bedding at the bottom is there to protect the pipe as we're placing it into it. So yes, you would need to be able to bring that in. So, okay.
Well, one of the cool things about that, Alan, is in the fourth generation of polyethylene resin, and the third for that fact, we can still get a point load, and it can damage the polyethylene, Alan, but that point load that's going to cause a stress riser and a leak in a polyethylene pipe will no longer run like it did in the first and second generations. So I met this gentleman from Garney who has an interesting story to share.
I bet it's great, Pete, but unfortunately we can't hear him. At least I
Oh,
can't.
you can't.
So I'll narrate as we go through. The thermal effects of HDPE make it so above ground in hot temperatures, that pipe can expand. And this gentleman had either was made aware of this and didn't recognize it, but or wasn't made aware of it.
Came back, the pipe be communicated to the site crew is that when this pipe gets hot, it expands. And we've noticed that along our right-of-way, we've actually got curls. We started the pipe straight, but it's expanded and kind of pushed the pipe around. We've also noticed that when it cools down and you put it in the ditch, it shrinks up a lot. So we had laid a string of pipe out one day and had left it a little bit past the direction the driller we were tying into. But we left it for the day as we were waiting for some other stuff. When we came back, the pipe had almost gone to 7 feet apart rather than 6 inches overlap. So we had to fuse on a small extra piece of HDPE to make up that gap, which wasn't a big deal, but it was something unexpected that we weren't aware of and could have adjusted for had we had that knowledge now. But just knowing that when you put that pipe in the ground, especially if it's a hot like it was for us in mid-August, then you're gonna probably have some shrinkage after you put it in the ground.
Well, Alex, tell us
Yeah,
All
so that's
right.
about the story.
quite a story there. Guys, if you wouldn't mind coming on and say goodbye, I want to say thank you to all of our people that took part in this webinar today. Most everybody stayed until the end. We're just excited to be able to share this, and we so appreciate the support you all shared with us. Richard Brand, great job for coming on today and sharing your stories at East Windsor MUA. And if somebody wants to get a hold of you, Richard, how do they connect with you?
They can either connect through me through my email, or they can call me direct at my phone number.
Pete, if
Awesome.
you advance 2 slides, we've got it right there too.
That
So
one day.
that'll
Well,
make it easier.
There we go.
Perfect.
There we go.
Thank you.
Yep.
And also, Dan Landy, could you come on and tell us how we get our PDHs or CEUs?
Yep, there will be an exit survey, and as soon as we close out the webinar, if you could fill that out, we'll get you everything you guys request.
Good. All right. So thank you, everybody. And thank you to our bench for asking and responding to all those questions. We so appreciate it. And we'll see you next time. We'll see you in April for our next round of webinars. Until then, we'll see you on the road. Stay tuned if you need a CEU or a PDH. Thank you so much.